recording now. So if you have any questions for Thiago, please feel free to type them in the chat or raise your hands at the end. And yes, so thank you very much, Thiago, for talking to us today. Thank you very much for accepting the invitation. It's over to you now. Thank you.
Well, thank you, Gustavo, for the kind introduction. Thank for inviting me for this talk, and thank you all for connecting. I apologize for the technical problems in the beginning. I am really not used to Teams. Sometimes I mess the things up here. But today I intend to talk about this topic relating microfabrication and the better understanding of the early universe. I intend with this talk put some perspective to the collaboration that we have between University of São Paulo and University of Nottingham, and which has been very exciting for us because we have been working on the edge of both sides, either in the radiation detector, which is the main topic of this talk, and in the additive manufacturing. So I am going to talk about a very specific point about the research we do about this kind of radiation detector, which is the new developments and exploitation of this of different techniques for microfabrication to produce new geometries of detectors and so on. But we are actually a part of a bigger project, including this kind of radiation detector. And basically, for this talk, I divided the content into three sections. Initially, I will give a brief introduction, why I'm talking about early universe, and I am combining this topic with microfabrication. Then I'm going to talk about the experiment that is conducted at CERN to explore the early universe. And then finally, I'm going to talk about microfabrication and how this is enabling a better understanding of the early universe. And to start with the introduction, I will start with the earliest beginning that we know. And in the early beginning, there was nothing, right? Actually, this is a point of debate between scientists. If earlier there was nothing or there was something, but to create some suspense in my presentation, I assume there was nothing, right? So in some point, a big explosion occurred, forming something that evolved and expanded in such a way that in the end, we have the universe as we know, right? Right after the explosion, what was formed is an environment with very high temperature, the highest temperature that we can imagine, even more, and a very high density of energy in this system. And as an explosion, this was expanding. And while expanding, the density of energy was reducing, the temperature was reducing, and lots of things happened. And in physics, when you have energy and nothing else, then you can imagine that lots of fundamental particles are produced, right? So in this very, very beginning, lots of quarks, antiquarks, muons, electrons were produced, but also many bosons, like the photon and like the gluon. And the bosons are actually particles that are responsible for the intermediate fundamental forces. The photon, for example, intermediates the electromagnetic interaction, while the gluon intermediates the strong nuclear force. When the system expanded, then the density of energy was reducing in such a way that the quarks could find each other and form some binding states. It can, one quark can form a bound state with an antiquark, forming what we call as a meson, or a triplet can be formed in a binding state of three quarks, forming what we know as baryons, right? The one example of baryon that is promptly found in the universe is the proton or the neutron. And in this point over here is where most of the hydrogen in the universe was formed, right? With more time, the system expanded more, and the baryons could find each other, forming, for example, the deuterium, the tritium, or even the helium, right? Evolving even more complex nuclei was formed, and some process occurring in the inner part of stars produced what we know today as the heaviest elements in the periodic table. Well, what is interesting is that this final part of this graph, I hope you can see my cursor, but this final part of this graph can be exploited either using nuclear reactors or low energy particle accelerators. But going back more into time, going backwards into time, it requires much more energy. That's why very large particle accelerators were built. If you see here in this graph, there's an arrow pointing to the specific point in time where the RIC accelerator, which was built in the United States, can explore, right? Then you see another arrow here, which is a little bit back in time, which is showing the point where Tevatron can explore. And there's a third arrow here showing where the LHC can explore. So you see that we spend lots of money, lots of investment, human resources, and so on, and then we can push this arrow just a little bit back in time. But back enough so we can understand more about the interactions that occur between those fundamental particles in such a way that they can form mesons and baryons. In this region in time, there is a complete mess, I would say, because these fundamental particles, these quarks and the gluons, are deconfined. This means that they are not bounded into mesons and baryons. And they form a state of the matter that we call the quark-gluon plasma, right? So in this plasma, the quarks and the gluons can move freely, and they are not forming any meson and baryons. And they exist in this unbinding state, and they can interact with each other. And this is what is interesting for us, because then we can understand better what are the most fundamental forces in nature. This is what is called the inflationary model of the expansion of the universe, right? And this can be exploited, as I said, in very high energy particle accelerators, like the LHC, the Large Hadron Collider. This is the largest particle accelerator ever built, and it aims the study of the subatomic world. It was built in the frontier between Swiss and France, and it was built more or less 100 meters down the ground, underground, and it's a very big facility. This main ring over here has something like 27 kilometers diameter. To achieve such a high energy that is required to do such experiments, then we have to produce the beam to the particle accelerator, introduce this into a smaller particle accelerator, accelerate this into some level of energy that it can be introduced in the intermediate size particle accelerator. And only after reaching a certain energy, it can be extracted and inserted into this main ring. And in some specific points of this main ring, you have 4 experiments optimized to study the subatomic world. One thing that is interesting about this particle accelerator, and it is something that is really amazing, is that you can accelerate 2 different beams going in opposite direction. Then, in this sense, you can accelerate protons in one direction and protons in the other direction, in such a way that in the experiments, they can collide. There is an intersection point between these 2 trajectories, so they can collide in these 4 experiments. You can also produce protons going in one direction and lead nuclei going into the other direction. Or a third option is producing lead nuclei going in one direction and lead nuclei going into the other direction. The intention here is actually having a simpler system, which is the proton-proton collision, an intermediate complex system, which is the collision between protons and lead, and then a much complex system, which is the lead-lead collision. But specifically in this experiment, what occurs is that the beam crosses, and this event can occur. So 2 nuclei, 2 baryons can collide, and the energy is so high that the electromagnetic repulsion is nothing. They can cross each other in such a way that the protons and the neutrons inside the nuclei, they collide in such a high energy, such a strong impact, that the particles that are contained within can be deconfined. This schematic is interesting to show that this collision may occur with some different distance between the centers, which we call impact parameter, so in such a way that some of the baryons act like spectators, and some of the baryons participate in the process. So, by deconfining these fundamental particles, what is formed right in this spot is what the quark-gluon plasma state. In a much smaller, in an infinitely smaller scale than what occurred in the universe, but enough for us to study this state. And the point is that the quark-gluon plasma formed in the collision can evolve in time exactly as the phase diagram I showed earlier, in getting into the hydronization state, so the mesons and the baryons can be formed, and the final particles produced in this evolution can produce some signal in the experiment that we can record. So by counting how many particles were produced, what was the type of these particles, the energy of these particles, then we can calculate back in time and then understand what happened during the KGP phase. And we do this by using different theoretical models, and then comparing, by comparison of what we measured and what is expected, we can confirm some theoretical models, or we can deny some experimental models. So this is more or less how the early universe is explored using the Large Hadron Collider. And the last thing I want to say is that we have here 4 different experiments, and something that maybe you may be wondering is why do we need 4 experiments? And the point is that each experiment is focused in a different point of the theoretical models. You have ATLAS and CMS, which are the most general experiments, and they are the largest also. And eventually you have heard about them because a joint measurement between these two experiments confirmed the existence of the Higgs boson a few years ago. You have also the LHC-b, it's a different experiment, and you have the ALICE experiment. And the ALICE experiment is the one experiment that is dedicated to the study of the KGP. ATLAS and CMS are dedicated to the confirmation of the standard model, and the ALICE is dedicated to the understanding of the KGP. So in this phase, state phase, is something interesting because you correlate fundamental physics in the sense of the standard model with hydrodynamics, electromagnetics. It's a quite interesting field to study because of this mixture of models. So I'll talk now a little bit about the ALICE experiment and how this is used to study the KGP. So the ALICE experiment is a very big experimental setup, which is composed of layers and layers of detectors. So you have here a schematic showing the beam coming from one side and the beam coming from the other side. The collision occurs right in the center of the experiment, and the particles produced in the collision, they are expand in the direction that is normal perpendicular to the beam direction. So you have you have here in blue the inner tracking system, which is one layer of detector responsible to determine the center of collision. You have the time projection chamber, which is this gray detector over here. You have the transition radiation detector. You have the electromagnetic calorimeter, and you have the time of flight detector. In the forward direction here, we just call it forward, but you have an additional experimental setup to measure muons produced in this direction over here. In today's presentation, I want to talk a little bit in more the details about the time projection chamber. This is the detector where I usually work. This is my work is aims to support the development of this detector, and this is a very specific point of my research. So how this time projection chamber works? All particles produced in the collision center, which is in this diagram represented by this red spot, they crosses this big barrel of gas, and when the particle crosses the barrel, crosses the gaseous media, it leaves behind a trace of ionization. So in each point you can find a pair of electrons and ions formed in the ionization of the gas. You have also a specific distribution of electric field pointing towards this central electrode over here in such a way that the electrons are guided to this end plate, which is this part over here, and the ions are guided to this intermediate electrode over here. The same thing occurs in the other side. If the trace is produced here, the electrons are directed towards this region and the ions are directed towards this region. Additionally, you have also a magnetic field that is responsible for bending the trajectory of the particle produced in the collision. By bending this trajectory, we can actually measure the radius of this trajectory, and with this radius measurement, we can determine the energy of the particle. Actually, we determine the momentum, but this is more or less, these are two variables that are correlated. But one thing that is important in this detector, and this is completely amazing, is that the electrons produced in this trace are directed into this end plate, where we have a positive sensitive detector in such a way that we can measure the projection of this trajectory into this plate. Not just that, we can also measure the time this electron spent to travel from the original point where it was produced until it collides with the end plate. So by measuring this time, and then we know that the electrons come here in the gaseous media with a different, with a constant velocity, then we can determine the position in the axial direction. And by measuring the trajectory, we can measure the actual, the radial position of the electron. So we can perform a 3D reconstruction of this trajectory, and then we can perform, for example, the measurement of the radius. As I said, the time projection chamber is actually the heart of the ALICE detector. I cannot say that this is the most important one, but this is definitely the heart of the detector. If you see this picture, which is the ALICE experiment open, the time projection chamber is this thing in the middle. Now I want to talk a little bit what happens with the electrons when it achieves the end plate, how this projection of the trajectory is measured. So in the end plate, what we have is a mesh of wires. So when the electron collides with a certain wire, then we can record which wire was that, and then we can record and then reconstruct the trajectory. So we have two meshes perpendicular to each other. But we also have this another additional mesh, which is it's called gated mesh. I will talk a little bit about this in a few moments. Well, two things are important in this kind of measurement, and is actually two different drawbacks of such a technology. The first one is called the ion backflow. When the electrons get closer to the wires, it feels an intense electric field that's going to produce an avalanche of ionization. So one electron approaching the wire can produce thousands of electrons in such a way that we can measure, we can enhance the signal for the electronics to record it. But what happens also is that this amplification leaves behind lots of ions in the surrounding region of the wires. And these ions are much slower than the electrons. They are thousands of times slower than the electrons. And this cloud of ions avoids new electrons to come to this wire. So what actually happens is that we must to record this, to turn this detector on and record the electron trajectory for some time window. And then we have to apply some voltage in the gated mesh in such a way that we avoid new electrons to come, and then we start what we say closed gate, where we don't measure anything. And this time window where we don't measure anything is necessary for the ions that were formed in the surrounding regions of the wires to dissipate. And this is not so good, because then we cannot measure this continuously. So we can only record events occurring in this time window. Anything that occurs here are not recorded. Another drawback is that these ions produced in the vicinity of the wires, they can get attached to the surface, forming a dielectric film on top of it. This gaseous mixture that are contained into this barrel very often contains what we call quenching gas, that can be CO2, CH4, and so on. So this carbon of this molecule can get attached to the surface, forming this polymer that reduces the sensitivity of the wire. This process can be recovered by some cleaning process, but this effect of ion backflow, creating this time window where you don't record nothing, is something unavoidable with this technology. So basically, eventually you have solved a figure like this showing data which was recorded by the TPC, which is all these trajectories over here. In the external part, you see these blocks showing the signal in the electromagnetic calorimeters. You see some moons over here. And you see that the TPC works a lot, right? Because you have lots of trajectories to record. And as I said, TPC is so important to the ALICE that it even appears in the ALICE logo. So one thing that is fundamentally important in the information provided by the TPC is the radius of this track, so we can measure the momentum of this particle. But we can also integrate along the trajectory how much charge was produced in the gas. And when we correlate these two information, when we measure the momentum using the radius and we measure the total amount of charge produced in the gas, then we can do a plot like this one, and then we can distinguish the many the different kinds of particles that are produced, right? So you see that in some point, most of these particles get together over here, and in this point is impossible to distinguish between them. And for this, to distinguish particles in this region, we use information coming from different detectors. But this is the information provided by the TPC. We can determine the momentum of the particle and the type of particle that was produced. The recent major breakthrough from the ALICE experiment was reported in this paper in Nature Physics, where we found evidences for the formation of the QGP in PP collision, which is something that was not expected so far. Data coming from different experiments had some indication, but it was not statistically significant. But the ALICE experiment was sufficient to confirm the existence of the QGP into this simpler system. Now I'm going to the topic of the talk, right? From micro to cosmos. How can we use microfabrication to enable a better understanding of the early universe? And this is all about the drawbacks of the multi-wire proportional counters, the multi-wire proportional chamber I mentioned, this mesh of wires. So we use microfabrication to avoid the problem of the gated mode and also the problem of the aging of the detector, the formation of this dielectric film. So we are replacing the wires, the mesh of wires, by something that is microfabricated. So we are using what is called a gas electron multiplier, which is a kind of philosophy of micro-pattern gaseous detectors, which was invented by Fabio Sauli. Here's a picture of him. So the gas electron multiplier is actually a foil of polymer covered by copper on both sides and microfabricated by producing a mesh, a pattern of micro holes over here. So this, in total, this foil has something like 100 micrometer thickness, and the diameter of these holes is something like 50 micrometers. We can produce this pattern in very large areas, and in the ALICE experiment, a stack of 4 foils are replacing the mesh of wires. So this is a photo showing the installation of this detector. This was already installed. They are in commissioning phase, and they are going to start operating during the run 3. That is going to start in 2025, I think. So this is an animation done by my PhD student, Thiago, showing how this gas electron multiplier works. When the electrons approaches the foil, it can be directed into the holes, and applying a potential between the 2 conductive layers, we can create inside the holes an intense electric field that is going to accelerate the electrons, producing the avalanche. And the electrons produced here are going to measure downstairs. And this animation continues with a higher velocity, so we can see what actually occurs with the ions. Some of them can collide in the surface of the copper, and some of them go upwards. This damages the signal because this is going to interact with electrons coming from different events. This is the ion backflow effect in the gas electron multiplier. Here we see the ions colliding in the surface. It can produce some aging effect. But what is important is that the electrons are amplified in the region inside the holes, but they are measured downstairs. So we separate the amplification and the collection regions. So this offers a much more robust system against the effects of the ions. So how these foils are produced? They are produced using standard techniques for microfabrication, using photoresist, chemical etching, and so on. And so you can produce such a pattern in meter square the size. But how does it improve the information we obtain from the early universe? Because with the gas electron multiplier, we don't need to run in a gated mode. We can measure particles continuously. So we can collect much more statistics. We can measure much more particles such a way that we can reduce the uncertainty bars in the energy in the invariant mass spectra, and then we can have more sensitivity to different particles. So in this graph, you show here the current status, or how the TPC use it to measure with the wires, the mesh of wires. And here is a simulation of how this is going to measure using the gas electron multiplier. So this particle, for example, is much better characterized. The amount of these particles is much better measured in this situation compared to this. So we are going to have much more sensitivity to fundamental particles than we can compare, which much better with the theoretical models. But here comes the collaboration between University of São Paulo and University of Nottingham, because we want to push this technology even further. We want to enable flexibility to prototype different geometries of the gas electron multiplier in such a way that we can solve some remaining problems, specifically those related to the aging and the ion backflow. For this, we are exploiting the projection microstereolithography. It's one specific kind of additive manufacturing. I'm not going to talk too much about this. You know this better than me. But one thing that is important, and you may be wondering, is that if the ALICE collaboration, we produce meter squares of detectors, how can we use projection microstereolithography for that? Actually, we're going to produce this in a much smaller scale, and then we can go to a research cycle. We design new geometries, we test them by simulation, we produce the prototype, and then we characterize. That's our intention. After, when we find the optimized geometry, then we go to a different stage of research on how to produce this in a larger scale. But this animation actually shows what we intend to do. The electrons coming to the holes, they will be amplified in the region of the holes. And in the left, I show what happens in the conventional geometry, and in the right, the modified geometry with the insertion of what we call here a decoration. It's a ring in the vicinity of the holes. With the electrons, there's not much difference, but with the ions, we see that the cloud of the ions going upwards is much less dense, and the trajectory of the ions when colliding with the upper electrode is much more restricted by the ring. So there are some differences, and we want to exploit these differences experimentally. Basically, we were well succeeded producing some of these hole meshes using 8DDA. The reproducibility of the holes is quite good. The resolution is enough. You see that there is a pattern of some artifacts produced by the resolution of the printing, but this is good enough for the prototyping. So what is interesting is that after producing by 3D printing, we can actually simulate what was produced. In this case, the simulation was trying to explore the effects of these resolution artifacts in the internal region of the holes. And what we see is that eventually we'll have something like 10% more ions colliding in this dielectric region, producing some charging up, and this has to be confirmed experimentally. We also did some tests involving regarding the production of this decoration. This was quite good actually, but we still have to work on this because now we have problems producing the conductive layer. Well, we have some trials of how to do that. Apparently, so far we were not able to produce the metallic film without introducing some contamination in the inner part, but it's still promising. This is ADS measurement showing that we did have some content of metallic material in the inner region of the holes. This is not good because when applying a different the voltages between the upper and lower layers, then a leakage current can go through the surface of the hole. So we have to solve this. One philosophy that we are considering is producing some caps in the holes and then only opening these caps after producing the foil. This is actually good. The projection microstereolithography can produce these caps, but we still have to work on this. This is still promising. Finally, what I'm going to show is that there is a lot of microfabrication that are suited for this kind of study, but on a joint research is done concerning the aging, because lots of tools to check the microfabrication can also be used to understand better the aging of such detectors. So basically, we want to understand the physics behind the process of aging, understanding the chemical availability after the avalanche, how these fragments flight, what happens during the flight until the electrode, and how this is absorbed at the surface. Here is an example of what can come from this research. This is a prototype of gas electron multiplier which was damaged by a spark, and using ToF-SIMS we can actually determine what was deposited on the surface of this copper and understand better what caused this spark that damaged the foil. This is more or less like a CSI study, because the foil is already dead, and what we want to do is find the reason of the death. Right? So here you can see the mass spectra what is contained in the surface, and deep inside the copper it is quite clean. So the information that we are looking for is in this spectra, this mass spectra. It's interesting because we could find this complex molecule attached to the surface, which is something that was not expected. It is an additional information compared to electron microscopy. This complex organic material is deposited in the vicinity of some of the holes, and this is actually indicating what molecule is correlated to the aging process. If we if we compare with different samples, we can actually see that this material can only come from the graded kapton, which is material used to the electric layer. On top of that, what we observed is that close to the spark region, there is a huge amount of this complex molecule. So we are blaming the death of this foil we are blaming this molecule to the death of this foil. So this brings my presentation to the end. So microfabrication is enabling a better understanding of the early universe by greatly improving the ALICE sensitivity to rare events. So the ALICE exploring the gas electron multiplier, which was microfabricated to enhance the statistics and then to understand better the rare events. The production of gems is challenging. Conventional innovative solutions are both difficult, but we are exploring additive manufacturing together with the University of Nottingham, since this is showing to be a promising tool. The conductive layer is still a challenge, but we are working on that. Also, the advanced material characterization is enabling a better understanding of the aging of these such detectors. And the micrometer resolution of 3D printing provided by the University of Nottingham will enable new and optimized geometries, so we can actually have some improvements for future experiments. So I hope I keep in time, and thank you for your attention.
Thank you very much, Thiago. Really, really nice talk. And you managed to stay on time despite the technical issues at the beginning. Well done. Thank you. So do we have any questions for Thiago?
Hi.
Hi, Jason.
Hi, it was a great talk. I have a question about the GM structure, especially the conductive layer. Is there any specific requirement of that conductive layer? For example, like thickness or certain level of conductivity?
Well, actually, I know that producing a very thin film doesn't produce a conductive layer. The point is that we have to produce a metallic film that has properties of the metal that is deposited, right? In this case that I showed in the ALICE detector, this metallic layer is something like 3 microns or something like that. It varies between 3 and 10 microns, not much more. I would say that it could be less, but there is some point regarding the addition of the copper into Captain. There is some technical issues there. I'm not quite experienced on this. I know that a very thin film can have less adhesion to the Captain. So this results in a foil that is going to be fragile, more fragile compared to the thicker one. And to be honest with you, I don't know the limits. What is the limit? This should be tested.
Okay, thank you.
Thank you.
Thanks, Jason. Do you have any more questions? You can use the chat or just come up and say.
Thiago.
Hi.
Thank you for presentations. I got a question is about the conductive layer as well. So at this moment it's using copper. So would you expect any impact if we use silver or gold? Would that make it better or worse?
From the point of view of testing, there is no difference for me. There's no difference for me. What can make some difference, and this is important, is regarding the aging process of the detector, because this changes the surface chemistry of the process, right? And to be honest with you, reading in the literature, copper is not the best material for that, because it's going to react spontaneously with CO2, forming already some geoelectric layer. So changing material is quite beneficial, I would say. Regarding testing new geometries, no difference at all.
Okay, thank you.
Thank you, Yufeng. Any more questions? So, Thiago, I have a question about the early part of your talk. I was just wondering, what's the typical time frame for one event? Because you say you have to detect many events, right? And just maybe a naive question, but how quick does it have to be for you to detect one event in the ALICE chamber? And in order to acquire statistical relevant data, how long do you have to run these experiments? Is it days or just hours?
This is an interesting question. I just don't understand if you're asking something like regarding how fast these detectors can be, or how long do you have to measure?
Yeah, I think both actually.
Okay.
It's about that plot you differentiate particles, right? So I can see you have to get many events, but I don't know how quick they are and how many you need.
I see. I consider both questions interesting because the first one is related to my work and the second one is related to general way this collaboration works. The first one is that when you have these particles produced in the collision, they expand very quickly. No detector in the world can follow how fast this can be. The point is that after expanding, these particles leave behind the signal, and the detectors collect this signal slowly. I would say that the TPC is the lowest one, right? It provides this very quality data, but it's the lowest one. Now, regarding the second part, which is how long to have to measure, and what is interesting here is that you measure this during all the time. Data producing in the first day of the LHC is combined to data which was measured yesterday, not yesterday, but the last day, because now it's not operating, right? So we can collect the statistics so we can conform the theoretical model. This is something that was you can see in the news regarding the discovery of the Higgs boson. Only after many years collecting data, they have statistics level to confirm the existence of the Higgs boson. So we combine all the data to have this information.
Really nice. Yeah, thank you. Really interesting. So do we have any more questions for Thiago? Well, I can ask another one, just my last
please.
one. So you're showing the files for the ALICE experiment, right? Because we never really discussed like the next step because we're still prototyping. But I noticed, I don't know if it's just that image, but it looks like the two middle files we have less holes. So like the first and the last one we have like the high density of holes, but the ones in the middle they look like they have less holes. Is there any reason for that?
Well, the reason for that is because they want to optimize the amount of ions that go back to the drift region. So lots of ions are produced in the avalanche, but the top layer acts like a filter to the ions produced in the lower foil, right? So in the previous technology, when using the mesh of wires, all the ions produced were going to somewhere, right? Avoiding new measurements. But in this new geometry, using different layers of gems, here, the ions produced in the holes over here, they are going to collide and be stopped at the lower conductive layer of the upper layer over here, right? So the top foil acts like a filter to the ions produced in the lower regions. I don't know if I made myself clear at this point.
So well, why would you have holes then, even if it's just a few?
Well, you must have different meshes because then otherwise you have a complete match between the holes of all. Then the ions can go through the holes and get into the drift region. So you do this to filter the ions to come back.
Okay, with the assumption that eventually some electrons will still make the avalanche. I see.
Yes, exactly.
Nice. Good, thank you. Last call for questions, everyone. Any questions for Thiago? Okay, let's check the time. That's perfect. Yeah, 3 o'clock. So if there are no more questions, we'll close the meeting today. Thank you very much, Thiago. That was really nice, really interesting.
Thank you
really nice
for joining.
to learn.
Thank you.
So yeah, we'll continue the collaboration, right? So we'll stay in touch, and yeah, thank you everyone for joining and for your patience at the beginning. See you next time. Bye.
Thank you.
Bye. See you. Thank you.
Thank you. Bye.
Bye.
Bye. it is too dry over here. I had to stop to drink water.
It's really hot. All right, so I'll leave this call to stop the recording, right? But we can catch up later.
Okay.
All right. See you. Thanks
See
again.
you. Bye.